In this tutorial, we are going to learn about chemical equations, but some specific types of chemical equations, namely dissociation equations, total ionic equations, and net ionic equations. And the one thing that all three of these equations have in common, or these types of equations have in common, is that they deal with how substances either behave or react in solution. And so one of the learning goals is to learn how to use a dissociation equation to represent what an ionic compound is doing or has done in solution. And we also want to find out what the difference is between a total ionic and a net ionic equation. So to explore these concepts, we're going to use the diagrams. We're going to create diagrams using using this legend. And so here we've got an Mg2 plus ion and two Cl minus ions. So this is what MgCl2 would look like in solid form, and this is what Na3PO4 would look like in solid form. But here we're asked to create an aqueous solution of MgCl2. And so it's important to recognize that when you add that, MgCl2 is an ionic compound. It is going to dissociate into its component ions. And so you're going to be left with one Mg2 plus ion and then two Cl minus ions in the solution. And we can represent that using a dissociation equation. And so if we have MgCl2, and this right here, this can either be as aqueous or it could be as a solid like we started out with. And we're showing then that when this dissolves, you end up with an Mg2 plus ion, and it's in aqueous solution, it's dissolved in the water, and you have two Cl minus ions that are dissolved in the water. And one thing that isn't shown here is the water, and so I've got the water, the diagram for water here, but did not include it to reduce the clutter. But here, for instance, with the positively charged magnesium ion, well, it's going to be the negatively charged portion, or the partially negatively charged portion of the water molecule that is interacting with this, so namely the oxygen part. And for these two parts here, it's going to be that positively charged or partially positively charged part of the water molecule, namely the hydrogen end, that is interacting with the two negatively charged ions. Either way, water molecules are surrounding each one of these ions, which is the reason why they are dissolved in the solution. And we could repeat the same thing with the Na3PO4 and find that we get three Na plus ions that are surrounded by water molecules, and we have the one PO4 3 minus that's also surrounded by water molecules. So when we combine these two chemical compounds, the MgCl2 and the Na3PO4, and they're both in aqueous solution, a chemical reaction happens. And you'll notice again that these are both ionic compounds, and so it's a double displacement reaction that takes place. And the nature of that reaction is that the two compounds switch partners, and so now the Mg, this positively charged ion, will be paired up with the negatively charged ion from the other compound, and here this positively charged ion, the sodium ion, will be paired up with the negatively charged ion from the other compound. And so I'm going to represent that in the picture down below, and we'll see what the products are. So we have each one of these Mg's is now going to be paired up with, and actually we've got something kind of like this. So we have one of the products is Mg3PO42, represented right here. And then we have a whole bunch of sodium ions and chloride ions. And so they're each going to form separate sort of molecules or formula units, if you will. But there's one difference here, one key difference between what happens with the Mg3PO42 and what's happening with the sodium chlorides. And that is that in the case of the Mg3PO42, this is a solid, it's a precipitate. We can use our solubility guidelines that we learned about earlier in the course to confirm that. But the NaCl is an aqueous solution still. So this new product, and we see everything is represented in this equation down below. The NaCl, we have 6 of them, and they're all in solution. And so really we should more accurately represent that by saying that, well, we've got a sodium ion and a chloride ion, and a sodium ion and a chloride ion, so on and so forth, because they're not bonded together. They're all separate. And so we end up with, as I said, this one unit, this one molecule, if you will, of the Mg3PO42, and then really it's 6 sodium ions and 6 chloride ions, but that's not completely represented using this equation down below. And so how we're going to better represent that, and I'll show you on the next slide, is by using the total ionic and the net ionic equations. So when we looked at MgCl2, we said that a substance like MgCl2, which is an ionic compound that is capable of dissolving in water, when it dissolves in water, we get Mg2 plus dissolved in water or an aqueous solution. We get 2 Cl minuses that are an aqueous solution. And that was the case for both of our reactants, the MgCl2 and the Na3PO4. They both dissolved in solution to produce ions. Well, in a double displacement reaction, ions can combine with each other to form new products and to form a precipitate, while other ions remain in solution. And it's these ions that remain in solution, the Na plus and the Cl minus ions, that are actually called spectator ions. Right? They're just kind of watching the reaction happen. They're not actively part of the final product, because if you think about it, we had Na plus ions on the reactant side, and we still had Na plus ions on the product side, and so there was no change that occurred to those Na plus ions, hence the name spectator ions. They're just there kind of watching on the side. And I'm going to maybe clarify that or show more evidence of that down below. So the equation that we saw, that we illustrated and showed in picture format, is right here. And as I mentioned before, not all of the ions are part of the solid material, right? There's still the sodium chloride, and it's an aqueous solution. So we said really it's Na plus and Cl minus that just remain in solution. And so we can maybe more accurately represent the situation using what's called the total ionic equation. And that's to show everything that can exist as ions is represented in that form. And so we have our reactants, and so we had in the balance equation we have 3 MgCl2s, and so we have 3 Mg2 pluses, and then we have the 6 Cl minuses, because we had 3 of the MgCl2s, but there are, in every MgCl2, there are 2 Cl minuses, giving us a total of 6 Cl minuses. And then we had the 6 Na pluses and 2 PO43 minuses for the same reasons I just described. But then on the product side, we had the Mg3PO42, and it doesn't exist as ions. It exists as in this form in the solution, we'll say in compound form as Mg3PO42 in the solution. And so we represent it accordingly, and we note the state is as a solid. But we mentioned that the 6 Na pluses and 6 Cl minuses are both dissolved in aqueous solution. And so we represent that. And this is what I was mentioning. If we take a look at these on the product side, and we take a look at the same things on the reactant side, we see that there hasn't been any change to the Cl minus or the Na plus. And so effectively you can kind of cancel those out from each side. And so that's what is represented in the net ionic equation, is the spectator ions are omitted because, as I mentioned before, there's no change involving those ions, and so they don't really need to be represented. Rather, in the net ionic equation, you only include the ions that are involved in the formation of that solid. And so in this case, it's the 3 Mg2 pluses and the 2 PO43 minuses, and those are the 2 ions that lead to the formation of the precipitate that forms, the Mg3PO42. one really important thing to note in for all of these equations is that they are all balanced. And so whether it's this kind of the typical equation, the total ionic equation, or the net ionic equation, all of the equations are balanced in terms of the amount of matter that they have and also the amount of charge. For instance, here I've got 3 magnesiums, and here I've got 3 magnesiums. Here I've got the 2 PO4 3 minuses and the 2 PO4s, okay? But in terms of charge, I've got on the reactant side 3 units of these, each with a charge of 2 plus, and so that's 6 positives. And here I've got 2 units, each with a charge of 3 minus, and so I've got 6 negatives. And so the total charge on the reactant side here would be 0. And the total charge on the product side is also 0. So hopefully in going through this tutorial, you have got a bit of a sense of what happens when an ionic compound dissolves in a solution and how we can use a dissociation equation to represent that. And then we've also seen when you combine ionic compounds, what happens to them in solution. And we see often it's a double displacement reaction that leads to the formation of a precipitate. Again, not all double displacement reactions lead to precipitate formation, but many do. And in those cases, we can represent those situations using total ionic and net ionic equations in addition to the typical equation.